Let's continue talking about NFAs. That's what we started talking about last time, and there's some homework questions concerning NFAs. And there's actually one thing about NFAs that I didn't tell you about. There's one thing that is allowed in an NFA, which is not allowed in a DFA. You can do all the homework problems, no problem, without knowing this, what I'm about to tell you. Huh? Oh, I'm scrolled. NFA. NFAs also allow what are called spontaneous transitions. Spontaneous transitions. Transition meaning the arrows, right? That's the technical word for what we call the arrows on a diagram like this. Spontaneous transitions, also known as epsilon transitions. And what this is an arrow on the diagram which doesn't use up any letter. That is, you could follow the arrow without even, usually like when you follow an A arrow, that means you read an A from the string. But an epsilon transition is one in which you can follow that arrow without doing anything to the string. So, for example, here is, and they look like, in the diagram, when you write the diagram, it just looks like an arrow that's labeled with an epsilon. How about this? Here is a nice NFA with two epsilon transitions. So this means you start here, of course, and then just like before you read anything out of the string, you can just jump to this one, or you can jump to this one. And if you jump to this one, it will be accepted, provided that you see only A's. And if you jump to this one, it will be accepted, provided that you see only B's. All right? So this is an example of an NFA with epsilon transitions. All right? And this one, what's the language? This accepts any string like A to the N or B to the N, right? Because you can either, after starting, you can immediately go up and do A's, or you could go down and do B's. But you can't do some mixture of A's and B's. Because once you go to the A's, there's no way to get back down to the bottom there. All right? That's so this is called, these are called epsilon transitions, and there's not a whole lot to say about them. Here's a slight variation of that diagram. What if I do the same one, but I put another epsilon here and everything else is the same? How about that? Can anyone want to say, like in words or at some kind of formula, what kind of strings are accepted on this one? So when you start, you can either go up here or down here, and then what kind of things will be accepted on this one? What do you think?
There could be any number of A's followed by any number of B's, or just a bunch of B's, but there can't be a B then an A.
Uh-huh, yeah. He said some words there. Some number of A's followed by some number of B's, where this number of either could be 0. I think is that the same as what you said?
Yeah.
I think so. So this one accepts, if I were to write that in a formula, I would say any string, well, how about X is in AB star, if you want to be fancy about it? Well, no. It's just some bunch of A's and then a bunch of B's, right? Any number of A's followed by any number of B's. This is how I would write it. And the N and M are natural numbers. So that each of those could be 0 if you want. You might wonder, looking at the diagram here, is the empty string accepted or not? Now, when you start here, it's not an accepting state. But actually, if you're reading the empty string, you can still do one of these epsilons and get to the accepting state, even if what you're reading is the empty string. So the empty string is accepted on this diagram, because after starting here, you can immediately do the epsilon, and you get to an accepting state, or this epsilon. Yeah?
What does the epsilon mean?
The epsilon on an arrow here means you can just do this arrow without using up any letters in the string. So it's meant, we use epsilon there because the epsilon also represents the empty string. So it's like this is a transition for no arrow, no letters. You go across this arrow. Yep. All right. These are called epsilon transitions or spontaneous transitions. You can do some cute tricks using the epsilon transitions. So there are tricks, epsilon transition tricks for combining NFAs. We talked about, there was that thing called the product construction, which can be used to combine two DFAs using a union or an intersection. There's ones on the homework for today based on that. There are similar tricks for combining NFAs, which are totally different the way they look. They're actually much simpler using these epsilon transitions. For example, if I have to get a union, for example, if I have this, let's imagine I have two NFAs. Here's one, I'll call this M1 is machine 1, and then machine 2 is this. Sorry, I left out the starting state. All right, what, if I were to say in words, what strings are accepted on these? Can anybody say? Like, just looking at the first one here, what strings are accepted on this machine? Yeah? Yeah, anything that starts with a B. You got to start here and do a B, and then you can do whatever you want after that. So this one accepts anything starting with a B. The language here I would write is like BX, where X is in AB star. I hope everybody's cool by now with reading things like this and making sense of this. This means all strings which have B followed by something, where that other thing can be any string of A's and B's. And then the second one, how would you describe the language of the second one? Yeah? Yeah, this one is anything that ends with a B. It says you can do whatever you like at the beginning, and then you finish with B. So this one, if I were to write this as a set, would be XB instead of BX. Again, X is in AB star. All right. Now, I haven't done the union thing. What about the union? That would represent, in this case, any string which starts with a B or ends with a B, right? That's the union means or. So the union would be, I want something which basically does this one or this one. And you can do this with a little sort of branching path of epsilons, just like up here, right? You can think of these two epsilons as sort of saying, well, you got to start here. You can either do this one or this one. And you can do that using any NFAs that you like. So the union would look like, I have a starting state, and then I go two epsilons, and then up here I'm going to put my first machine. Sorry, I had to scroll it away. And then down here I put the other one. Come on. Like that, right? So what you see here, if you like, this was my first machine, M1, and this was my second machine, M2. This, as far as getting the union, this is far easier than getting the union of DFAs, right? Because that requires you do the product construction, which you make all those pairs. It'll take you a while. This is a lot simpler way of getting the union of two machines. All right? Using the epsilon transitions. It's a cute trick, and it's very simple to do if you're allowed to use the epsilons. That's why this doesn't work for DFAs, just because you can't use the epsilons for DFAs. All right. Unfortunately, I will just say no similar cute trick for intersections. We can talk about intersections eventually, but there is no easy way to get in an intersection of two NFAs by using epsilons. There's another type of cute trick that you can do with epsilon transitions, and that is we can also do concatenations. This is another way of combining together two machines. So concatenation, anybody know what that word means? It's a fancy word. Probably see in programming, maybe? I don't know.
It's like combining, right?
It's like combining somehow. Yeah, specifically concatenation for strings is you put one string at the end of the other one. You just like jam them together. So concatenations, in terms of languages, this would look something like, can I do all strings of this format, x, y, where x starts with B and y ends with B. How about that? I'm trying to do a concatenation of our two simple examples up there. All right? You may be tempted to read this as an intersection because it kind of says x starts with B and y starts with B, but this is not an intersection. It is this format of word followed by this format of word. I said word, I meant string. It's this kind of string immediately followed by this other kind of string. That's a concatenation. And how do we do that? Well, to do that for my two NFAs, I want to do something kind of similar to this, but I'm going to put the two, like these two machines, instead of going in parallel, sort of you can do this one or you can do this one, I want to make it so that you got to do one of them and then followed immediately by the other one. So the way to do this, I will draw sort of a schematic first. You do it like, you have your M1 here, and then you make an epsilon and go into the M2. So that means in order to make it all the way to the accepting state here, you have to first go through the first one and then get to the accepting state in the second one. So in our particular example, what that's going to look like is my M1 was this, right? This was the M1. Now, the original M1, this was accepting, but actually I don't want to make this accepting anymore because I want to make it so that the only way you accept the string is if you go through both of them, M1 first followed by M2. So this is not going to be accepting. Instead, this will have an epsilon going into the starting state of M2. And then we do the M2 machine looked like this. And now I'll have a real accepting state. So this is the M2. So you take the accepting state from the first one and tie it with an epsilon into the starting state of the second one, like this. All right? So this is a simple way to get a concatenation of two languages using the epsilons. Or a concatenation, well, I said two languages. Two machines, two languages, whatever, using the epsilons. All right? These are nice little tricks that are, there isn't a similar one for DFAs because the epsilon just makes it more convenient. All right, let's just try one other example. How about, let's make an NFA for all strings where let's say the total length is even. And no, or the number of A's is even. Maybe I'll let you try this. I'll give you a few minutes. My hint is this word or here means you should do the or trick, or the union trick. So make a little machine for each of those things first, and then tie them together using these epsilons in the appropriate way. See what you think. I want the alphabet to be A, B. I suppose I should have said that. Looks like people are doing fine. I'll write my answer up here. No spoilers. All right, can we talk about it? As I was walking around, it looked like people were doing great on these. So these are the two individual machines that I came up with. The one on the left is the one where the total length is even. You just go back and forth every time you see any letter at all. And this one is the one where the length of the number of A's is even. You go back and forth only when you see an A, but if you see a B, it has no effect on anything, which is to say you just stay where it is. We've done this evens, odds things. Basically, if something involving evens versus odds, you want two states where it goes back and forth in some way. So these are my two machines that I'm going to combine in this kind of two branching paths thing. So this one looks like this. This is my first one. And my second one looks like this. There you go. I think that'll do it. I hope you got something like that. Any questions about that? I suppose you could have done it a little bit differently, but you shouldn't have. Yeah.
I know it wouldn't really make sense to do for this one because there's only 2 letters in the alphabet, but like, could you theoretically do an arrow with like the symbol being like the whole alphabet, like the sigma thing?
We wouldn't write it that way, but I mean, yeah, you could if you want to. To me, the sigma, I would be concerned about the sigma looking like this.
Yeah.
But yeah, I mean, if it was A, B, C, D, I would just put A, comma B, comma C, comma D. That's a little annoying, but that's how I would write it. Yeah. All right. Excellent. Okay, those are some basic NFA tricks with the epsilons. We're going to talk some more about this in the future, but I think that's good enough for now. What I would like to talk about briefly, we're not going to get too fancy about this, but I do want to talk briefly about NFAs formally. The formal description of an NFA. This is something we have talked about for DFAs. Every DFA, technically speaking, is just like a 5-tuple of stuff. And an NFA has basically the same ingredients. It has the set of states, it has the alphabet, it has the starting state, it has the arrows, and it has the set of accepting states. So the formal description of an NFA is not all that different from the formal description of a DFA. The difference is, I would say, differences of NFA versus DFA. I would say, first of all, NFA has epsilon transitions. This is something that a DFA doesn't have. And another thing that is true, or that is different, is an NFA, like the principal difference is, the NFA can have 2 outgoing arrows with the same label on them. And what that means is, the function that, like the transition function, like the little delta that we use for a DFA, it may not have just a single answer. Like, where do you go when you read the letter A? Well, on a DFA, you just go one place, but on an NFA, you could go several different options. So the other difference, the major difference is that we may have several outgoing arrows. With the same label on them. And the effect of that is, so something like, delta of Q comma A. This means if you begin in state Q and read the letter A, where do you end up? In an NFA, you could get more than one answer to this, right? Where do you end up is, maybe you could end up here or also over here. This can be a set, not just a single answer. You could get, say, 2 different possibilities for where you could go from this state if you read A, all right? So this is the major formal difference, is that the answer of the delta in an NFA is a set rather than a single state. And it can be any set. It could even be the empty set. That would represent, if you have no outgoing arrows, then this delta thing is the empty set, all right? But otherwise, it looks the same. So I think we can just sort of write this down, and then we'll talk about the interesting differences when they come up. But so here's the true definition of a NFA. An NFA is a 5-tuple. This will look the same as a DFA. Q, sigma, delta, Q0, and F. Where, I will tell you what each thing means, but it means the same thing in a DFA. Where Q is the set of states, and it has to be a finite set. So Q is any finite set. This is the set of states. Sigma is another finite set. This is the alphabet. Delta is the transition function, and here is a difference. This is going to look super technical. I'll write it down first and then we'll talk about what it means. The domain and the codomain of the delta are different from what they used to be. I will just remind you, maybe I'll write it up here in green. For a DFA, the domain and codomain look like this. This means what you plug into the delta looks like a pair consisting of a state followed by a letter, and then the answer is a state. So this was for DFAs. This is going to be more complicated though because, so one thing that makes it more complicated is the letter could also be epsilon, because you can have an arrow that has an epsilon on it rather than a letter. So the the domain here, instead of Q cross sigma, it's Q cross sigma union epsilon, like that. So this says the domain is pairs where the first thing is a state, a little q, and the second thing is from this set, which is to say it is either a letter or a epsilon. That's what this, there's no easier way to write that. That's what this set means, sigma union the set containing epsilon. So this is the set of either a letter or a epsilon. That's the domain. And then what is the codomain? So in the case of a DFA, it was just you get as an answer a state. But here we can, as I said a moment ago, the answer can be a set of states. It's not just a single state. It is a set of states. So what I need to put over here is the set of all sets of states. That's the codomain. And this, anybody remember a fancy word for that from discrete math? It's the set of all subsets of something or other. That's what I'm talking about here. There's a name for that set. Maybe nobody remembers. Yeah, you remember?
The kernel.
No, that's everything that becomes zero.
Power.
The power set, yeah. So that is typically written with a fancy P. The power set. So this is power set of Q, which means the set of all subsets of Q. All right. So this part indicates that transitions either use a letter or epsilon. That's what that little union in there means. The part that you put in that coordinate, in that part of the pair, this is a pair, a Q comma something else, it's either a letter or it's the empty string epsilon. And this thing over here, this big power set of Q, it means the answer, is a subset of Q. That is, the answer is a set of states. It's not just a single state. It's a set of states. All right. This is the difference. The delta here looks very complicated. This is the kind of thing you can, this is like Hollywood mathematics. They love things like this. They would throw in some infinities. They love the infinities. I know. All right. Can we just, for the sake of completeness, describe the other two ingredients? So we said the Q, the sigma, the delta. Sorry, I'm off the top here. What about the Q naught and the F? They are what you think they are. So just like in the DFA, the Q naught is the starting state, and the F is the set of accepting states. So just to finish it off, Q naught, technically it is just an element of Q. This is the starting state. And then F is a subset of Q, and this is the set of accepting states. All right. So I would like to do an example where you translate a NFA diagram into this formal stuff. There were some on the homework about DFAs. It's not at all hard to do. You just have to know the correct sort of formatting to use when you write your business. So let's try, how about this is one of those ones that I used a moment ago. I'm going to call the two states Q0 and Q1. Actually, maybe I'll call them Q1 and Q2. Doesn't really matter, but I'm going to go 1s and 2s. And the arrows are like that, and this is an accepting state. So this is a very simple NFA. And I want to try to write the formal description. Let's say this machine is called M. So I would say M equals, and I'm going to write my 5 ingredients here. The first is the set of states, which in this case is Q1 and Q2. So first goes the set Q1 comma Q2. All right. Next is the alphabet. What's that in this case? Yeah, the set of A and B. Wonderful. Next is the delta. Now, as usual, when I'm doing these, I'm not going to try to squeeze the delta. The delta is an entire function. So down below, I'm going to say where, and then describe the delta down there. Next is the starting state, which in this example is Q1. This is technicalities, but you should not put the little curly guys around Q1. That's because what you write in this position is supposed to be a specific state, not a set of a state. So this is just that state, not a set. And then finally, the last thing is the set of accepting states. This one should be inside a little curly guys, because what goes in the final position is supposed to be a set of states. So it is a set simply of Q2 by itself. All right, yes?
How would you write that in L of N?
We're going to talk about that in a moment. Yeah, let's just finish writing the description of the deltas, because the delta is a little weird if you want to get it fully correct. So I have to write all possible evaluations of the delta, and remember what goes into the delta, what you plug into it are pairs, where the first thing is a state, and the second thing is a letter or an epsilon. So the possible inputs would be, I could do Q1 and A, I could do Q1 and B, or I could do Q1 and epsilon. And then I could also do Q2. I'm just going to write all the possible ones, and then we'll say what they actually are. Q2 of A, Q2 of B, and Q2 of epsilon. And then for each of these, you need to say what the answer is. Come on now. So what about Q1 and A? That means, where are all the states we can get to? So the answer will be a set. Where are all the possible states we can get to if we start in state Q1 and you read A? So you should look here and look for outgoing A arrows. I see no A arrows here. What does that mean? The answer is? I see some people just kind of shaking their heads. You cannot go anywhere. So what I'm supposed to write here is the set of all states which you can reach by reading A from here. And what is that set? Yeah? It is the empty set, yes. So this is the empty set, which I'm going to write like that. That means your interpretation of that is there's no A arrow from the state Q1, right? That's why that one is the empty set. What about Q1 and B? Well, from Q1, if you see B, you can get to Q2. So the answer for this one is Q2, but it has to be a set. So it's this, the set of Q2. All right. Next one, Q1 and epsilon. From the diagram, you can see there is no epsilon transition here, and so that is also the empty set. There is no arrow with the epsilon in the original diagram from Q1, so that's also the empty set. All right, Q2 and A. From Q2, if you see A, you can go back to Q2 and nowhere else. So the answer to that one is the set Q2. Sorry, I got to scroll the picture. From Q2 and B, if I'm in state Q2, I can do B and end up back here. So that is also Q2. And again, there's no epsilon there, and so the epsilon is empty. All right. There you go. This is the formal description of this NFA. Any thoughts about that? Here's a question. Did anybody think I should have written like this? Since these are supposed to be sets, should this have really been empty set in a set thing? Because they're supposed to be sets? What do you think?
It's already called an empty set, so I don't think it should be.
Yes, you should not put those curly things around the empty set. Not in this case, at least, because the empty set is a set, even though it doesn't have those curly things around it. If you additionally put this around it, then now this means the set containing the empty set, which is not what I'm talking about. It's just the empty set. All right, you almost never want to talk about the set containing the empty set. Sometimes, but that's pretty weird. Almost never what you actually mean. All right. Somebody asked a few moments ago, how can we express the language accepted by the NFA using this formal description? So what about the language? What about the language of the machine? Written in the formalized language. Now, I will just remind us, so it's going to be similar to what the DFA said. I will remind you over here. For DFA, it said the language of M is the set of all X in the alphabet star, where delta star of Q0, comma X is an element of F. So remember what this means. The delta star means it's like delta, only you do an entire string, not just a single letter, but you read an entire string. And this means if you start in the starting state and then you read the string X, where you end up is in one of the accepting states. That's what F means. So I would like to more or less write the same thing. You can actually more or less write the same thing, but we need to talk first of all just briefly about what does delta star mean in our case. So in the case of NFAs, if I do something like delta star of Q comma A, sorry, X, this means starting from state Q, where do you end up if you read the string X? So this is the same thing from a DFA, the only difference is you have to keep in mind that you may end up more than one place. When you read a string in an NFA, it can end up in several different possible finishing states. So this is defined to be the set of all possible, I'll say all possible destinations if we start at Q and read the string X. All right? That's a set. But once you understand what that is, then you can basically write this same thing again. So then, sorry, it's going off the top there. It's the set of all strings such that delta star of Q0 and X. Now actually we have a little problem right here. Maybe don't write this, what I'm about to write is not quite right, but the original one said is an element of F. There's actually a problem with that. Anybody have an opinion about why this actually is not is no longer really legal to say here. It has to do with the difference between the DFA thing here. On a DFA, this is a single state that you end up in, and then you can say that state is one of the accepting states by saying it's an element of, sorry, I'm off the top, it's an element of F. What's the problem with this? You got an idea?
There could be a way that you do it, like there could be a way where you could end up in the accepting state, but also a way where you don't.
Yeah, right. When you start in the starting state and read a string, remember there are many possible states you can end up in. The rule is the string should be accepted if one of those is accepting, right? But there's a lot of them. So you can't say element of here because actually this is not a single thing. It's a set of things, right? So this is a set. That means you can't write this as an element of F. It's a set of states. So you might think you could, instead of element here, write subset, right? That would make sense. But this actually is not what you want. This means, if you write this, this means all of the possible destinations, all of them are accepting states. But that's not the requirement. The real definition says not all of them are accepting states, just like one of them is an accepting state, all right? So this you have to say, maybe it's most clear if you just write in words. This thing contains an element of F, all right? Because that delta star thing is a set of states. They don't all have to be accepting states, but one of them has to be an accepting state. And so that's one way that you can say this. That thing contains an element of F, all right? Now, if this was, if we were, you know, in a Hollywood film production, they would love all this until that. They're like, nah, man, we don't want to see words in your math. We don't like that. We love this delta star. That looks pretty awesome. But this you can write. They would say, come on, man, you gotta use words there. Actually, if you want to look cool in front of your friends, you can write it this way. And they're gonna love that too. So this says delta star as a set intersect with the set of accepting states is not empty. That means there is some element in this intersection, which is to say some element of F actually is also in this set, which means this contains an element of F, all right? This is the very, very fancy symbol way of writing that right there. So if you want to be maximally confusing, you should write it this way. Otherwise, write the words. All right, this is the formal description of what the language of an NFA is. Now, maybe I'll just say, as far as, say, homework problems or quiz or test questions go, if I ever ask you, describe the language of this DFA or this NFA, I almost never want you to write this stuff. Usually, if I just show you an NFA and say, tell me what the language is, I want you to say something like, all the strings end with B or something like that. If the only reason you should be thinking about this is if I say specifically like, show me the formal description of the language or something like that. Just like if I ask you to give me an NFA for a certain language, I don't expect you to give me all of this stuff. I expect you to draw the diagram. So unless I say specifically, I want you to do this in terms of the formal description, you usually don't have to write the language in this way. All right. There were some homework questions for tonight about, you know, describe the language of the machine using sets. I don't want you to say all of this stuff. Just say it's the set of all strings with whatever. All right? Let me know if that's unclear. I would be happy to clarify. All right. Great. What do we got? We got 30 minutes, right? We finished at 1:45. Okay. I would like to discuss our next kind of thing is really, I mean, I've mentioned a few times, like everybody knows there are differences between NFAs and DFAs. But the real question in terms of the differences between these things is what is the, how about computational difference between NFA and DFA? Like NFAs, I would say, have more capabilities because an NFA can have like extra arrows, and it can also have epsilon arrows, and it can also have no arrows. It can have missing arrows, right? So I will say NFA allow more, more kinds of machines, right? Like actually every, I don't know if I've said this before, but it's probably you gathered. Every DFA is automatically a NFA, right? It doesn't have any epsilons and it has all the arrows. But there are some NFAs, of course, which are not also DFAs. So NFAs allow more kinds of diagrams. So does that mean that NFAs are capable of calculating more types of languages, right? What kinds of languages can you make with a NFA versus with a DFA? So NFAs allow more kinds of diagrams. Can they compute different languages? Or is it the case that like giving these extra features, extra types of diagrams actually doesn't really make anything any more capable? It's just a different way of drawing diagrams. All right, that's the question that I want to talk about. So I will just say what I just said out loud. I'll write this down. Any DFA is automatically an NFA because NFA are just, they are allowed to do more stuff, but anything that a DFA can do, an NFA can do the same diagram. So any DFA is automatically an NFA. What that means is that NFAs can compute any regular language. Remember, regular language means a language that a DFA can compute. I haven't used that word in a few days, but that's what regular language means. It's something that you can do using a DFA. And since every DFA is automatically an NFA, that means the NFAs, they can compute any of those regular languages, but are there any other fancier languages that you can do with an NFA but you cannot do with a DFA? The answer to this question is no. I don't know if this sounds surprising to you, but to me this was a little surprising when I first learned this basic fact. The answer is, I will just say actually, NFAs cannot compute any more languages than DFAs. Even though they look fancier and they are technically allowed to use certain types of arrows that the DFAs are not allowed to, it turns out these extra features are not enough to actually make it be able to compute any other fancier languages. All right, and it turns out actually, yet more actually again, I'll say actually twice. I got tenure, what are they going to do? Actually, any NFA can actually be converted into an equivalent DFA. And that's what I want to talk about for our remaining time together today. NFA can be converted to an equivalent DFA. So it means the NFAs, they do have more features on the surface, but it turns out like everything they can do, actually the other one can also do. They have the same capabilities. And this is kind of a theme in this course. We're going to talk about a lot of different types of machines. And the question you should always ask yourself when presented with a new kind of machine is, I mean, this looks different from the other one, but maybe they are actually just the same. Maybe everything you do on one, you could also do on the other one. It's like Mac and Windows, right? Like, they're different. But at least in theory, whatever you can do with a Mac, you can also do the same thing with the Windows. And in fact, if you really want to get specific about it, you can run emulators or virtual environments in which you can run a Mac inside of a Windows, or you can run Windows inside of a Mac. You can run Windows inside of Windows. All of these would demonstrate the fact that these are two systems with the same capabilities. They just look different on the surface. All right. It turns out the same is true for NFAs and DFAs. Any NFA can be converted into an equivalent DFA. And I want to talk about how this can be done. There is a general purpose method. For example, I'll just give you an example first of all. Here's a NFA that we talked about earlier today with some epsilons. Right? This one, the language is A to the N, B to the M. That one on the surface is definitely not a DFA because it uses epsilons, right? And it has several states with no outgoing A's or B's. But this one there is a DFA which does the same thing. So this one actually is equivalent to this one here. I'm going to impress you by drawing an equivalent DFA It's a bit more complicated, I would say. Oops, sorry. This thing across the bottom should be going all the way like that. Sorry about that. All right, it's more complicated, in my opinion, a lot less clear. If you asked me to look at this diagram and say what is accepted, I think I could more or less immediately say it's any A's followed by some amount of B's. Whereas this one is a bit more complicated in my opinion, but it does accept the same language, all right? And in our remaining 20 minutes, I'm going to show you there is actually a general purpose procedure for which, if you know how to do it, you can start with this diagram, and completely by following a specific procedure, you can create this diagram automatically, all right? There's a specific process for converting a NFA like this into a DFA like this. And in this particular example, this is the picture you'll get if you do it properly, all right? And this is referred to as the subset construction. This is what you use to convert. This converts a NFA to a DFA, an equivalent DFA. It's called the subset construction. And it is similar in, it feels similar at least to the product construction, which we talked about a few times ago. This is called the subset construction. And the idea is the subset construction converts a NFA to a DFA. So I'm going to, just so that I can do this example more specifically, I'm going to write that same NFA, but I'm going to give names to all the states. Let's call them, how about X, Y, Z? So this is my NFA diagram that I started with. Y and Z are both accepting states. All right. And I'm going to, from there, I'm going to build a new machine, which is a DFA that's equivalent to the first one. And the way to build it is the DFA states are subsets taken from the NFA. That's why it's called the subset construction. Remember, in the product construction, the states that you create are pairs, and it's called product because that's in set theory, the product of two sets is the set of all the pairs, right? So in the product construction, you get pairs. In the subset construction, you get subsets. from the original machine. So the states that I'm going to be using are going to look like, the set of x and y, or maybe the set of y and z, or maybe the set of z by itself. There are a bunch of subsets, all right? So I will try and tell you how to do this. So we start with the starting subset in my machine. In my opinion, this is a little harder to do than the product construction, but it's easier to mess up, just make careless mistakes. We start with the set of the starting state together with all states reachable by epsilon. So, what is my starting state in the DFA is a set of some stuff. Which stuff exactly? It would be the set including x together with any other state that you can get to by doing epsilons, which would be actually in this case x and y and also z. So in my case, sorry, maybe I'll try and put this guy nearby. Oh, come on. I want to make a little one. No. This over here. Shrink it. Yeah. All right. Okay, so my starting state will be as a set x, y, and z all together. Every state in this machine looks like a subset of states from the original machine. And we start with the set consisting of the original starting state, which was x, together with all the states reachable by epsilon from x. And if you look on the original diagram, that was x, but also y and z together. All right, and now that's my starting state. Sorry, my pencil. And then we draw the arrows. Now, this is supposed to be a DFA, which means it has an A arrow and a B arrow everywhere, right? So I'm going to have an A arrow and a B arrow going somewhere. I happen to know they're going to two different places in this example. How do you say where the arrow goes? You look at all of these states, x, y, and z, all of them, and you ask, where can they go if you do A? Now, if I start in any of these, x, y, and z, now you might say, can you just get to any of them again after doing A? That's not actually true. If you start in any of x, y, and z, can you do an A and end up back in x? I think actually you can't. If you start in any of these and you do an A, you cannot end up back in x. I would say you can end up in y by doing an A. Can you end up in z by doing an A? Well, not really, but you can do an A followed by an epsilon, and you can end up in z. So this one is going to go to yz, and maybe I'm going to scroll down and write the rule here. So for each arrow, here is how you make the arrows. To make the arrow, you find all possible states where we can end up by reading the appropriate letter. And also epsilons. So this is the rule for how you draw the arrows. You find all possible states where we can end up by reading the letter of the arrow you're drawing and also allowing epsilon. So in this example, if I start from x, y, and z, and I want to draw the A arrow, the question is, what are the states I can end up in if I start in any of these and I do A and also possibly epsilons? And the answer is, I can start in y and do A and end in y. So y is in here, and also I can do start in y, I can do A, epsilon, and that's why z is here. All right. What about the B arrow? You look here again and ask yourself, starting in x, y, or z, where can you end up if you read a B, also perhaps including epsilons? Anybody think you can see? if you like, you could go through them one by one. Can I end up in X after reading a B from any of these? I don't think so. What about Y? What about Z? What do you think? Yeah? She says Z. I agree. You can only end up in Z, starting from one of these three and read a B. The only place you can end up is Z. You can never end in X or Y. So this one goes, so technically it's the set containing Z, but those are just labels for the states, so really it doesn't matter what you write in there, but it is the set containing Z. All right, and now we just have to keep on drawing arrows until we fill out the whole diagram. So you can continue, let's continue from here. I want to draw the A arrow from here and the B arrow from here. So from Y and Z together, if I do A, where can I end up? So looking only at Y and Z, if you do A, can you end up in Y again? I think yes you can, because you can do Y, goes back to Y. Can you end up in Z? The answer is yes, because I can start in Y and do A epsilon and end up in Z. And so YZ, the A arrow, goes back to itself. Because from either Y and Z, if you do an A, you can again end up in either of Y and Z. All right? What about the B arrow from YZ? Any thoughts? Yeah?
Just Z.
I think the answer is just Z. Yeah. From Y or Z, you cannot end up in Y by doing a B, but you can end up in Z by doing a B. So that arrow goes there. All right? All right, I like that. How about, all right, we need arrows from here now. Looks like maybe we're almost done, although each arrow, this arrow could go into a new state, which we haven't talked about yet. From Z, let's do the A arrow from Z. Where does that go? If I see, starting in Z, what are all the states we can reach by reading an A? Yeah?
Is it nothing?
Nothing, yes. What exactly do you mean by nothing?
Like there wouldn't be an arrow for A? Or...
There must be an arrow because this is a DFA, so we need an outgoing arrow, yeah.
Empty set.
The empty set, yeah. Every state here represents a set, and for a typical example, there will be a state representing the empty set. So in this example, we need a new state here representing the empty set, and there's an A like that. Because from Z, if you read A, what is the set of all states you can reach? The answer is there are no states you can reach, which means the set that you're looking for is the empty set. And what about from here, the outgoing arrow with a B? From Z, if you read a B, I can end up in Z, and that's it, I think, right? Even following the epsilons, you can't get to those other states. So the Z arrow with a B goes back to itself. Okay, we need outgoing arrows from every state. So we still need 2 outgoing arrows from the empty set state. So this is a little strange, but what this says is, starting from nowhere, if you do an A, what are the states you can get to? There's only one sensible answer here.
Just empty set?
It is still the empty set, yeah. So actually when you do this, if you use the empty set state, it always has looping back arrows for every letter. Because starting from nowhere, where can you get to? The answer is nowhere. And so from the empty set, it only goes to the empty set. All right? Excellent. We are pretty much done with this example, right? The only remaining question, like I've filled in all the arrows, and there are no more arrows to do here because every state has an A and a B arrow. The only remaining thing is, how do we decide what should be the accepting states? And the way to choose the accepting state is any state that you see here which contains one of the accepting states should be accepting on this diagram. And so I'm going to write that in words. So the accepting states are any subsets containing an accepting state. From the NFA. All right. So in this example, the original NFA accepting states were Y and Z. And so on my diagram, everything which has a Y or a Z should be accepting, which is almost all of them, right? It's this one, and this one. Those are the accepting states. All right, and that's my final answer. Any questions about that? Yes?
Can you go back to what you wrote? I didn't finish writing.
Yeah, sure. The accepting states are any subsets containing an accepting state from the NFA. All right, and I would like to bring to your attention this answer that I got here. Check it out. I'm going to try and, can I scroll it out enough? Not really. Remember this? I wrote this a few minutes ago. Does this look familiar? That's the same DFA, isn't it? We came up with the same diagram by doing that procedure. So the moral of the story is I can give you any NFA here, and if you do that stuff, you will come up with a DFA which is equivalent to the original NFA. You don't even have to think about, okay, what's the accepted language here, and then rethink that language in terms of a DFA. You don't really have to do any of that. All right. Let's just do one more, and then I think we'll be on our way. Any questions before we try another? All right, let's just go for it. I give you a NFA, and your job is to convert to a DFA. So it helps to have names for the states. I'll call this one STU. How about that? It's a little easier when there are no epsilons. This one, if you like to say what language is accepted here, this accepts any string where the second to last letter is A, because this says you can do whatever, but in order to get to the accepted state, you can do anything you want, but you got to finish with A followed by something. So that means the second to last letter has to be A. But you don't even have to think about that. In order to convert to, this is a NFA, convert to a DFA. This is your job. You should expect a test question about this. I mean, it's pretty straightforward. If you remember the procedure, you just do it. So anybody want to suggest, what should our starting state be? It should be a set. But what is it? Where do we begin?
Just the set being S.
Just S, yeah. Remember the rule is your starting state is the subset consisting of the original starting state together with anything which can be reached by epsilon from the starting state. But there are no epsilons here, so we just begin with S. All right? That's my starting state. And now let's draw the arrows. They may loop back, or they might go to some other state, in which case we'll have to just add a new state into the diagram. Let's look at the A arrow from S. You look at, from S, where are all the states you could end up by doing an A? Someone want to shout it out? Where could you get to? S and T, yeah. You can, from S, by reading A, you can come back to S, or you can go over to T. So I'm going to make a new state over here, S and T. And that's my A arrow. Oops. All right. What about the B arrow from the starting state? From S, where can you get to if you read a B? I think the only place is back to S, right? So that's going to be a looped edge like that. All right. I'm feeling good so far. Let's talk about S and T then. From S and T, read a A. What do you think? Someone else want to shout it out? Starting from either S and T, where can you end up if you do A? Someone else want to shout it out? Yeah?
STU.
STU. I agree. Yeah, you can end up in S here, you can end up at T like this, and you can end up in U like this. All right, so I have to make a new state for STU. I'll put that over here. Stew. Okay, what about the B arrow from S and T? What do you think? What do you think?
S and U.
I would say S and U. From S and T, you can get back to S. You can get to U here. You cannot get to T. by reading a B from S or U. So ST, I guess I'll have to put that down here. B, S, and U. All right. Okay, let's do the arrows from S to U. So that means from anywhere, if I do A, where can you end up? I think the answer is anywhere, right? From any of these, if you do an A, you can end up back in any of them. So my A goes like that. And then the arrow from B, S to U, doing a B. From any of these, if you see B, I think you can get to S or U, but not to T. So I would put the B arrow like so. All right, are we done here? No, what else do we got to do?
The accepting state.
Okay, you have to indicate the accepting state. Actually, there's more that we have to do. Yeah?
SU.
Yeah, more arrows from SU. Remember, every state has to have 2 outgoing arrows, a A and a B, so we need arrows from SU. From S and U, the A arrow, what do you say? It's almost time to go. You want to shout it out? I hear someone whispering it. From S and U, I think it's just S, right? If you are in either of S and U and you do A, you can't do that from U, so the only way is from here. S goes back to S. So that arrow goes like this. I did this ahead of time and positioned my states in the cutest possible way. And what about the B arrow from here? S and U, if I do a B, I can come back to S, and that's it. So this one also is labeled with a B. Now I think I'm done with all the arrows and states. Yeah?
For the A arrow there,
Uh-huh.
would it not be ST? We go back to S and then go to T also.
Yeah, I got that too.
Yeah. No, I think you're right. I was going to say, how dare you question me? But yes, you're right. You should feel free to question me. Yeah, this A should have gone up like that. Yeah. Anybody disagree? I think that's right. Thank you. I have it wrong on my paper. I don't know why. Like I said, it is kind of easy to mess these up just because you didn't see something or other. Last thing is to indicate the accepting states. And remember, the rule is any state containing one of the original accepting states should be accepting down here. The original is U, so anything down here with a U in it should be accepting. And that would be here and here. And that does it. All right, we'll do maybe another example next time. And then I do want to talk about why this works. This is a bunch of nonsense, which hopefully you believe me at this point that these machines are actually equivalent, but I think we should talk a little bit about how you know. All right.